Does it look like an ice cream cone to you? Or does it look like a brave red trumpet for playing music? What are you looking at is a three-dimensional illustration of the electric potential generated by a point charge. If the charge is positive, the value of the potential is positive, and if it's negative, then the potential is negative. Every electric charge generates an electric field. For a positive charge, the vector field is directed outwards. On the contrary, if the charge is negative, the field points inward to the charge. These are the contents that will explain the electric field and potential for a point charge. Feel free to jump to the specific part that you need, or you might just go with the flow. The easy-to-use description for this kind of electric field invokes the use of spherical coordinate system. In Cartesian coordinate system, a point in three-dimensional space is described by the values of x, y, and z. But, in spherical coordinate system, they are replaced by the radius r, the polar angle theta, and the azimuthal angle phi. This is very useful because the electric field of a point charge is, by nature, radial. Yes, there are occasions where it is more useful to apply Cartesian system, but that's beyond the scope of this video. And what is the mathematical expression? The electric field of a point charge is this constant within the parentheses, multiplied by the charge q, divided by r squared, where r is the radial distance from the charge. The sign of the charge determines the radial direction. If it's positive, the field lines point in the same direction as the radial unit vector, r hat. But if we flip the sign to negative, the direction becomes antiparallel with respect to the radial unit vector, and the field lines point inward. For both positive and negative charge, the magnitude of E is inversely proportional to the square of R. This is what we call the inverse square field, another example of which is gravity. Now what is the electric potential at a distance r? It's this, a simple scalar function. But how do we derive this formula? This starts from potential difference between 2 points. Let's call them P1 and P2. I will explain it to you right away with a simple example, which will bring forth to you a very important point. The potential difference does not depend on the specific path taken, but on the coordinates of the endpoints of the path integral. Look at this picture. There is a point charge and we want to calculate the potential difference between P1 and P2. We will take two different paths. The first is the green path or the direct path, while the second one will be the blue path, starting from P1, turning right to P3, then straight to P4, and turning left to P2. All points are described in polar coordinate system. The radial distance from the origin to P1 and P3 is a, while to P2 and P4 is b. At the same time, the angle from x-axis to P1 and P2 is alpha naught plus alpha, while to P3 and P4 is alpha naught. The electric field has only radial component, E sub r, while its angular component is 0. This fact will be very useful during the integration process. For the green arrow path, it's pretty straightforward. Expand the expression for the dot product and execute the integration. Because the angular component, E sub phi, is 0, then the contribution comes solely from the radial component, which is this integration. Let's call this V sub AB. Next, let's do the 1, 3, 4, 2 path. This can be broken down into 3 subcalculations, namely V sub 1, 3, V sub 3, 4, and V sub 4, 2. For V sub 1, 3, the radial component contributes nothing because R sub 1 is equal to R sub 3. At the same time, the angular component of E is 0, thus making the result 0. Calculating V sub 3, 4 is the same as calculating V sub 1, 2. Its result is V sub AB, which is equal to V sub 1, 2. V sub 4, 2 is also similar to V sub 1, 3. The absence of contribution from both radial and angular component makes it 0. Therefore, we can simplify the expression of V sub 1, 3, 4, 2 by writing the right-hand side as simply V sub AB. Because V sub 1, 2 is equal to V sub 1, 3, 4, 2, It has been demonstrated that the potential difference only depends on the endpoints and not on the specific path taken. If we hold R1 fixed for arbitrary values of R2, then the potential difference becomes a function of R2 only. In electrostatics, it is convenient to set the reference point, R1, at infinity. Let's set R2 equal to R and see what happens. We execute the integration procedure casually, and by doing so, we obtain the potential V as a function of R. The fun thing about electric field and potential is that we can derive the electric field from the scalar potential function. We use the gradient or nabla operator written in proper coordinate system. Here, because the potential field is specified in spherical coordinates, it's appropriate to use nabla operator in spherical coordinate system. Calculating the electric field is not so difficult for this case. The potential function has no polar or azimuthal components, so only the radial component remains alive. This will be useful if you come across a complicated charge distribution and you don't want to mess with vectors. What about the blue and red cones at the beginning of the video? They are visualization of the potential function. The radius consists of just x and y. The z-axis is used to plot the potential value. This video is the first of a multi-video series covering the topic of electric field. We will discuss more exciting topics in the future. Don't forget to hit that subscribe button so that you won't miss even a bit. Thank you.